Welcome to session number 6 in the series Microwave and Millimeter Wave Circuit Designs. I'm Anurag Nigam, and in this series 6 I'm going to talk about on-chip passives, the lumped elements on chip, right? So first thing I'm going to talk about is an inductor model. So how do you put an inductor model together very quickly? Whether it is a series inductor or a shunt inductor, and then how do I do a series capacitor and a shunt capacitor model. So let's get started with doing this modeling, right? So we know some of the formulas which we have covered here, right? This y parameters. So these y parameters are going to be used for modeling a inductor. So let's go ahead and lay out an inductor on chip and then model it, right? So passives, I'm going to make a new schematic and call it inductor 1 nanohenry, right? So I'm going to make a series inductor 1 nanohenry, right? So I'll add series to it. So I'll make a series inductor which is 1 nanohenry. Okay, now I'll tell you this, that no matter what you do, even if you have an inductor, right, or a capacitor, the ground port has to be continuous between the two ports. The ground has to be continuous. It's not that you will remove the ground and you will have an inductor or a capacitor. That's not advisable, because you will have a very huge ground debouncing loss at high frequencies. So it's, even if you put a thin line as a ground between input and output port, you need a ground continuity, right? Otherwise your circuits are not going to work at high frequency. So let's go ahead and pick up so I opened a schematic, which is kind of stupid, but I should have opened the layout. So let's see if this is created. Yes. So I would say new layout. Okay, so I'm creating a layout for that. So already the grid information is already there. Now I'm going to pick up a part. Okay, now I see here there are spiral inductors and then there is a square inductor. So let's have a look at this square inductor. Now what that is, okay, I'll tell you what this is. Okay, this PDK designer, okay, is not doing any maths in here. Okay, what he has, I think he has discrete inductors, means they have separate S parameter files, okay, which they got from either measurement or from simulation, right? So am I going to believe him? No, I'm not going to believe him. I'm going to derive it, right? So let's look at the inductor. Now a second thing is, he doesn't mention what frequencies he is specifying this inductor value, right? So it is 0.25, 0.2419 picohenry. At what frequency, right? That's the question. So let's say this is the closest one to 1 nanohenry, right? Okay, and they are, I think, giving current capability also as 1 ampere and stuff like that, right? Status data verification. Yes, okay. R sub is 16.92 ohm, C sub R series 1.18 ohm, and LSR 160.79 picohenry. What is that? Self inductance, inductor LPR inductance. Okay, anyways, it just says that here we have got this fixed width 7, spacing 7, inner radius is 40, I think, and number of turns is 3.5. now I'll tell you this, if you put more the number of turns you put, more will be the DC resistance. First we will check what these guys are claiming. Okay, so I'm going to put here a inductor which is huge. Okay, so let's see what is in this inductor. So I am going to flatten it, component flatten, and one level of hierarchy. Okay, so I want to see what is this. So this says this is span. Okay, so it means that it's going to have air underneath. So if you look at the substrate, okay, there is this 2.3 micron of air, and the top metal is 4 micron, isn't it? right? So the top metal 2 is 4 micron, and there is a 2.3 micron of air, right? So this is the air. So between metal 1 and metal 2, there is going to be a air bridge. That's what it is, right? Okay, anyways, let's see what is this. So this is metal 2 drawing, and what is this? This is metal 1 drawing, and what is this? This is VR2, right? So that is stitching metal 1 and metal 2. Anything else? Nothing else. And this is called when we do LVS. Okay, so there is no relationship between a trace of, there is no distinction between a trace of a line and an inductor. So how would you do LVS, right? Because LVS, if you do extraction, the extraction will not tell you that this is an inductor. It will just say there is nothing in there. It's just a trace of line, so it will say it is a trace of line. So you have this ghost layer, which is basically for LVS purposes, declaring that this is some kind of an inductor. So I'm going to undo. For now, I'm going to undo this. Okay, and I want to do simulations. So what I'll do is, let's look at the substrate. Okay, so we have 50 micron of gallium arsenide. Now the question comes is whether you want to keep everything coplanar on the layout. So at high frequency it is preferable to keep everything coplanar, right? Or whether you want to do everything microstrip, then impedance control on the chip is difficult, right? So let's first of all just put here metal 1 and reference everything to that metal 1, and I'm going to put in here, just randomly put in here metal 1, right? And I am going to just center it out. So this is the center, and here it goes, and I will just shrink it to its level, right? And then I want to keep the same dimension everywhere, right? So let's just do this. Okay, and I want to keep the same dimension. That's why I am doing this on the ground plane. Okay, so that is equal now. Okay, so now let's put the ports. So I have port 1 which goes in here, and then I have port 2 which goes in here, and then I'm going to have port 3 which goes here, and I'm going to have port 4 which goes here. Okay, so now I'm going to just replace move this underneath. So I will move this underneath here and remove this port line. So this is done. Similarly, I'm going to move this one underneath and remove this line. So now I have set the ports. Okay, now I'm going to go to EM and create EM setup, and in this EM setup I am going to do a FEM. Okay, so before that let me just set the ports. Okay, so go to substrate. So substrate definition here, ports. So in this port definition I am going to do open a port editor and take 3 as a ground reference for 1 and 4 as a ground reference for 2, right? So once that is done, I am going to open back the EM simulation, save it, and let's see what's the problem here. If I do this FEM, everything looks okay. Okay, so lesson learned from the previous session is that let's rely on 3D simulator rather than a 2D simulator. Let's do both. Let's see what it turns out to be. Okay, I'm going to simulate in the frequency of my interest. Let's say I want to go up to X band, let's say 12 gigahertz, right? So I want to simulate from DC to 12 gigahertz, or rather second harmonic of 12 is 24, third harmonic is 36, so fourth harmonic is going to be So I'll go to third harmonic. So let's say this is 36, correct? And I have DC point included. Okay, so the next thing I want to do with this is I am going to save the data for all the frequencies, and I am going to mesh. So I'm going to say, once you have done with the best mesh, so use that. After convergence, solve on the finest mesh, and then I will ensure that EM model is generated, and I will say save. So I am doing FEM rather than I'm doing MOM, and I will do MOM, but I want to see how different they are. So let's hit a simulate button. Okay, so first it is going to do the substrate computation, isn't it? So by the way, by the time it is doing, let's look at the 3D EM preview of this inductor. So it's doing something. It is also doing 3D EM preview. Okay, where is my inductor? Metal 1 is there. So all the metals are there. Why don't I see this? Oh, it's too small. Okay, so look at this. This is what it has done to the extent of the port. Okay, so this is what it has done to the extent of the port, and this is going to the mid, right? Okay, let it be, because I usually dependent on momentum to do this, but first time I'm kind of referring to this one. Okay, so what you can see in this inductor is the following. You have port 1 and port 2. So let's see port 2 what is happening. In case of port 2, you are coming as an underpass, and in between there is a air, which is going to consider air pocket, right? And it has tied. Okay, so what we have come up with a mesh refinement. Okay, so it has stitched metal 2 to metal 1 everywhere using VR2, and then in this place there is a underpass here which is coming out. Okay, so let's see what this is going to be. So for now I'm going to put the recording to pause, and once the result is done, I'll come back and show you, right? Okay, seems like the simulation has finished and we have some S parameters, right? So I want to extract what this inductance was. The kit says that it is 1.2 some nanohenry, right? So the kit says that this is 1.216 nanohenry, right? At what frequency they haven't specified. So let's see what it is. Okay, so I'm going to go to the results, and over here I have plotted S11 and S22, and it has hit resonance here. So it has hit resonance at what frequency? So this is usable up to 25 gigahertz, but this is the 25 gigahertz is the resonant frequency. Okay, is it usable up to there? No. Marker new. Okay, so we are talking about the other side of the port, right? Sorry, not this one. M2. Why M2 is not moving? M2. So this is going up to 21 gigahertz only. Now let's see. So what I'll do is I'll write some equations. I will say ys is equal to s toy s. So I have converted this to s parameter. Then I'm going to write the equation for the inductor. So in the inductor will be ls is equal to imaginary of 1 divided by minus y12, right, divided by 2 pi frequency, 2 into pi into frequency, right? So that is ls. What's wrong with this? Maybe it didn't accept this y this way, so it basically needs a this is y12, so imaginary of that divided by that. Oh, still no error message is there. Why is it not taking? Okay, so this is called ys. Mistake is mine. Okay, so this is your inductor. So let's look at the inductance. Go to equations and look at ls. And yes, it is close to 1.5 Henry. It's slightly more. And how come it didn't become negative? It is supposed to become negative, isn't it? Because it looks like a capacitor beyond this point, right? Beyond 25 it should look like a capacitor. So imaginary of 1 over minus y12 divided by 2 pi frequency. So I don't know what is going on here, but let's look at what this value is. This value is 1.54 nanohenry, 5658. So at 10 gigahertz is roughly 1 nanohenry. I am not sure why I didn't get the resonance point here. Okay, maybe it's the shunt capacitance which is doing it. It's not the series capacitance, or it's not the so this is the capacitance to the ground which is doing this. So this is not a resonant frequency. So resonant frequency is much higher. So the capacitance to ground is the one to blame here. Okay, so let's look at what is the DC resistance. So if I was to put a marker here at DC and look at a 50 ohm system, okay, so I'm getting 51.024. so 1.024 is the DC resistance. Okay, so now let's try to model this. So we got our 1 nanohenry inductor, a series inductor, and this is the shunt capacitance is too high. That's why it is rolling off, right? So let's try to see what is the shunt capacitance. So I will do one more thing. I will put here RS, Control C, Control V, and this would be the series resistance RS, which is RAC plus RDC. So this is RS. Okay, so this is going to be real of that. So this is going to be real of this. Okay, so now the real of this I'm going to plot in a different plot. So this is going to be the resistance part. Equation RS. Okay, so resistance, okay, it starts at 1 ohm. So marker new, it's going to start at 1 ohm. So this is RDC. So M5 is RDC. Okay, so Control C, Control V. Okay, so RDC is equal to M5. RDC is equal to M5. Correct? So RDC is M5. So I am going to plot here RDC. Okay, so this is your that, and RAC will be RS minus RDC. Okay, RS minus RDC. RAC is equal to RS minus RDC. Okay, and that I'm going to plot here too. Equation RAC. Okay, so this is your RAC. This I'm going to make green color. Okay, so we have inductance and series resistance. Now let us look at the shunt capacitance. So CSH1, which is because of port 1, right, on the port 1 side. So CSH1 is going to be equal to imaginary of YS11 plus YS12, isn't it, divided by 2 pi frequency, divided by 2 into pi into frequency, right? So this is CSH1. So let's plot CSH1 now. Okay, so CSH1, equation CSH1. Okay, so now here I'm going to look at a typical number, marker new, and here I'm looking at 42 femtohenry, right? This is 42 femtohenry. Okay, similarly I will have CSH2, control C, control V. So CSH2 will be YS2, 2, right? 2, 2. And I will repeat this over here as the graph, and here I'm going to change this to CSH2. Okay, so that I'm looking at as 29. That I'm looking as 29 femtohenry. So right hand side has a lower capacitance to ground on port 2. Okay, now the next thing I want to see is RSH1 and RSH2. So select this, control C and control V. Okay, so I'm going to do this as RSH1. Okay, and this will be the real of this, correct? And there is no frequency dependence, and 1 over that, 1 divided by that. So this is RSH1, so I am going to put it here as RSH1. Okay, so to me, okay, so what I'm going to do is I'm going to put this on a log scale, because the DC part is open, right? So no loss at DC. That's why it is going to show you infinite something, right? Okay, so here I'm going to put a marker and it will give me, so I'm not seeing. Okay, so let's put here a marker new. Okay, so this is around, so let me put here engineering. So this is around 158 kilo ohm is the loss. So let's zoom in. Okay, so that's what that is. And this resistance is, this leakage is dropping up to 7k. Okay, oh sorry, leakage is increasing up to 7k here. Okay, so this leakage is also a function of frequency. Now control C, control V. Okay, RSH2 is going to be equal to 2 comma 2, right? And I am going to repeat this. Okay, so this is going to be RSH2. Okay, so of course if this is a measurement data, I am going to see lots of this stuff, right? So don't worry about that. So at 10 gigahertz I can see, at 10 gigahertz, so that is the closest to 10, 266 kilo ohm. And this at 10 gigahertz is 191 kilo ohm. And this one, CSH1 at 10 gigahertz is again I'll put an engineering mode here. Okay, 42 femto. And this one is going to be 29 femto at 10 gigahertz. Okay, 29 femto. Now if I was to do a broadband model, right, let's also look at the inductance value. This is also engineering mode. So this is 1.064 nanohenry, and this is this thing. Okay, so now if you want to do the modeling, okay, I really want to know what is the resonance, okay, because this L should become negative to know the resonance, and I'm not seeing that to happen. What instead I'm seeing is that these capacitances are way too high for this inductor to be used beyond a certain frequency. But still I'm interested in what is the resonance, so I'm going to simulate it for a longer time. So I am going to go here to the simulation, go to simulation setup. Okay, and I am going to go to frequency plan, and I want to simulate up to, so 48 gigahertz, correct? And I'm going to hit simulate. So let me see if I'm recording and you are seeing what I'm doing. Yeah, I'm recording. So at this point I'm going to hit simulate and say yes, doesn't matter, and now I'm going to put it on pause on recording. Okay, so now it has simulated up to 48 gigahertz. Now you can see that the inductor is still rising, but I'm expecting that somewhere here there would be a resonance, series resonance, and that frequency is roughly around 49 or 50. This RAC, or RS. Okay, so that basically falls off. So let's see this RS. Let's see what is happening to this one. So yeah, this basically falls off, goes up to like 100 ohm as the peak value, and then falls off. Okay, so it indicates that resonance should be around here, 48. Now let's go ahead and put the model for this inductor. Okay, so I will go here into, I will make another new schematic, and I will say test inductor, right, create schematic, right, and here I'm going to do a lumped equivalent. So I'm going to put here a inductance, and that inductance is whatever that value is. whatever that value is. Okay, so this value is going to be 1.061 nanohenry. So 1.061 nanohenry, correct? And then I'm going to put here a DC resistance. So the DC resistance is M4 or M5, right? Okay, yeah, M5, 1.027. So this is going to be 1.027. 1.027. Fine. And then I need a AC part of this resistance, which is going to be a function of frequency, right? So I'm not sure if I can put here directly a function of frequency, but let's say whatever is the remaining I'm going to put here. So at this point, marker new. So this is a subtraction term is RAC, so green one. Okay, so I hope it is on green one. So this is M10 RAC. So RAC at 10 gigahertz roughly. RAC is 2.7 ohm. Okay, so this is going to be 2.7 ohm. 2.7 ohm. So overall it's going to be 3.7 ohms, right? Okay, so later on we'll write a equation for that. Next is I am going to put a capacitance across it, right? And that capacitance, okay, that capacitance is going to be 48 gigahertz. From 48 gigahertz I will compute that capacitance. So I will go here and say CA, anti-resonant, is equal to, okay, so it's 1 over 2 pi root of LC, right? So 1 over 4 pi square, 1 divided by something, isn't it? So that something is going to be, 1 divided by 4 into pi into frequency, right? And so just one second, pi into resonant frequency, and I'm going to assume here to be the resonant frequency, right? So this is roughly 46 gigahertz, right? So it will be 1 over 4 pi frequency square. So it will be 46E9. 46E9, right? Into L, right? 46E9 square. So this thing I have to square it. So I'll put it in the bracket and do a square. So the square is double star square into, it's going to be L value, right? So that is going to be 1.061 E9, E minus 9, sorry, isn't it, right? So this should be the anti-resonant capacitance value. Let's see what that capacitance value is, CA. Okay, equation CA, it is around 1.28 fem or 11.28 femto. 11.28 femto. So the shunt value would be 11.28 femto. 11.28 femto. Okay, so this is the capacitance, and then I'm going to put the shunt capacitors. Of course there is frequency dependence on it, but I am going to put them flat because I am not going to make it so involved. So one side, input side, is 42.56. Okay, so 42.56. So this is port 1. Here it is 42.56. Okay, so 42.56 femto. So I'm just gonna copy this, say 42.56, 42.56 femto, and the other side is going to be 29 point, other side is roughly 29.6 femto, 64, 29.64. So the other side is 29.64, 29.64. Okay, by the way, I don't see that there is any book which teaches this modeling, so this is going to be the only source for you for modeling this. There may be some papers. So this is what, 29.64. So let's correct that. So 29.64. Correct. And then there is a leakage to ground. Again, it is going to increase with frequency, but let's put it flat. The flat is 128 on the left hand side, 129, and 146 on the right hand side. 129 and 146 K. 129. I think that's what the correct number is, right? Okay, 129K. Let's see this. 129K and 146K. So I'm just going to repeat this. 146K. 146. Okay, now having done this, okay, let's do a S parameter simulation 0 to 48 and see whether it looks similar, right? So I'm going to put here what you call a port, S parameter. I'm going to put here a port. Now who might like to do this model? Okay, people may just use a S parameter file, right? But if you want to improve your inductor in a process, you should know where your resonances are coming from. So probably I can advise these foundry guys that this 42 and 29 is way high. So they had to do something underneath the inductor, like like we do in silicon or silicon germanium. We do glass underneath, right? Here it is just the substrate, right? So it's basically the substrate which is in between, which is doing it. Okay, so and the reason may be in the simulation itself, right? Okay, so let's do S parameter simulation going from DC to 48 gigahertz. DC to 48 gigahertz. Sorry, 48 gigahertz. In step size of 1 megahertz is okay. Say okay, okay, and let's hit simulate. Okay, let's look at S11. Okay, it's doing that, and this is 1.074. Let's look at the S11 from EM simulation. So that would be called inductor this, and this is adaptive. So S11 from there. Okay, so this is the blue one. The blue one is your this thing. So 1.026. Just 1 second. Marker new. What is the DC resistance here? look into a 50 ohm system. Format 50 ohm. This is 1.027. Why did I? That's what I have put here. Oh, that frequency dependence term, right? Of RAC, right? So this RAC is coming as 2.7 because it is put as fixed, right? So that's not what we are supposed to do. So we have to put in here a formula for this, right? So a linear approximation, so we have to go square root of frequency, right? Is there a square root of frequency term that will bend over, right? So let's put here the slope, right? 1.27 to 1.2.7, right? So 2.7 is the difference, right? And that is over what frequency? 10 gigahertz, right? So if I divide by 10, okay, so let's try to write a formula here itself. Let's divide this by 10 E9, right? So that is the slope, and multiply it by frequency. So that's a linear approximation, isn't it? Will it accept it? I think it should, or it will complain. You see, you cannot put that equation here. Okay, can I put this in bracket? I think not. Okay, so now I have to go to equation based linear. Go to equation based linear. Equation based linear. Where do I see that? Equation based linear. Let's pick up a single Z. Single port. One port. This is two port. Okay. Then okay, so let's ground 2 and 4. Let's ground 2 and 4. Okay, and let's put this in here. So let me just copy this, copy, paste, and same value I will put here in S12, paste, isn't it? And I'll replace this. Now it should not complain. Okay, so if I do simulate, oh, maybe it didn't work the way I thought it would. Just 1 second. F4. Okay, so instead of using 2 port, I'm using a single port here. Now what do you see here? When I do this and I look at this, it looks like this. So now it is starting at a right point, but there is this variation. This variation which you are seeing, the red one is taking longer to cross because the capacitance value is going down, isn't it? And that's why this extent is also less. So basically the capacitance value is doing this. Now let's also look at S22. S22, right? So this is S22 from the, this is S22 from the model, and let's look at the S22 from the EM simulation. Adaptive S22. Okay, so the magenta, let's make it the green so that it is visible. Okay, so the green with the magenta and the blue one with the red. So this is measured versus, or EM simulated versus modeled, right? Is this fair enough, or do you want to really match the high frequency side? Well, we will see. Let's look at the inductance. Okay, so in this case I would have to write the equation for inductance here. Okay, so that will be little problematic, but let's do this. Okay, so I can copy the same value. So if I go to my data set and if I take this, so all this basically, so edit, copy, and then I'm going to go here and do edit, paste. Okay, so now I'll plot inductance. So equation inductance. Okay, so I have seen the clear this thing. I'm seeing clear this thing, but I need inductance from the EM simulation also. Control C, Control V, and I will put here EM. Okay, so EM. Okay, and in this case I will make this, I'll do this, Control C, Control V, YS1, and here I want to add the S parameter. So I want to add the S parameter from my adaptive. So from this adaptive there is S. Okay, so here I have to put YS1, isn't it? And then the frequency will also come from there. So sorry, because this frequency line will not match. So if I go here, there is no frequency, there is. Okay, so now I'm going to put here LSEM. LSEM. Okay, so now you see that this is not matching. This capacitance, right, is way too high. The capacitance is way too high, or maybe the shunt capacitance drops. The shunt capacitance drops with frequency. So this shunt capacitance drops with frequency. This is what you observe in the EM simulation, or increases with the frequency, right? So shunt capacitance is increasing with the frequency. So let me see here. Okay, I want this to match that. So let's bring down the capacitance. Okay, how much? Let's see. This is the capacitance, right? Okay, let's see how much capacitance I have to bring down. Okay, and here you go. Okay, there it is. So I will update this schematic and close. Yes. Okay, so now this is measured versus model of an inductor, right? So S11, S22, right? And this is going to be show up in the phase of S21, right? So there is a minor difference here in inductance value, but it is modeling it correctly. Okay, so now what remains to be seen is the series resistance RAC. Okay, so this is RS, right? So let's do this RS for the EM simulated. Control C, Control V, and here I will do YS1, isn't it? And I'll plot the two RSs. Okay, so because I'm doing linear approximation for RS, but it has to be proportional to square root of frequency because the skin effect should come in, right? So let's put here RS first and RS1. Okay, so you see here RS is for the model, and with the linear there will be a square root term come here, which will cause this to fall off, right? Isn't it? So it will not be proportional to frequency. It would have this fall off also, right? So I will reduce it by square root of frequency term, right? So go here. Now I have something to share with you. These deep learning and AI guys, I kind of have an allergy to those people, because what they do is they will put a training sequence here, right? And they would say, I would finally have a model without doing anything, without any physical insight. I will have a model, correct? That's what the deep learning AI people do. They will just do a random run, and they have no physical significance whatsoever in their model. They will put in the training sequence and they will come up with a model. And that is where the whole of the world is going. They are substituting modeling with this iterative technique of theirs. This kind of hurts me. Okay, this kind of hurts me. Okay, why does it hurt me? Because you are misguiding young generation. Okay, and if there is anybody in LinkedIn who wants me to take up me on this, you are welcome. Oh, this is too heavy. Okay, so this is too heavy. And second thing, this should also have this term, right? 10 gigahertz, right? So this comes far later, right? You see. Okay. So okay, it's too much. Okay, it is affecting that also. Probably I will leave it at this value when it comes close. Okay, I have to get it even closer. Okay, so I think I'm gonna leave it over here. Okay, more or less. I just want to go as close as possible, right? So if it was 9, I know this is not correct. There would be a fraction which has to be subtracted. No, this will be 5 only. So let's go here 5. Okay, this is still way negative because reason is that this frequency has to be subtracted sometime. So okay, so that's not going to work. Sorry. Okay, so up to here it is going to 150 ohm and this is going to be 100 ohm. So there has to be a correction over here somewhere, right? There has to be a correction over here, right? So I'm going to leave it to that because I'm okay in this range where I want to model this, right? So let's look at S11 here in dB, and let's look at the S11 from the EM simulation in dB, and let's see how bad that is. So it's not bad, it's fine. And let's look at the phase of S11. Okay, and let's look at the phase from the EM simulation of S11. Okay, there you see. Okay, so you have to make a reason for this. Why the phase will do such a big difference? So this one is okay. S11 phase. Let's look at S21 phase. S21 magnitude first, and then adaptive S21 magnitude. So that's matching, and let's look at S21 phase. S21 phase, and let's look at S21 phase from the adaptive. S21 phase, so kind of matching here. S21 is matching, S11 magnitude is matching. Phase, I still have a problem with the DC side, right? Okay, and S22 and S22 dB from EM simulation. Okay, so I am going to leave that model here because this is the very quick turnaround for a broadband model for an inductor. I think I can use this inductor up to 30-35 gigahertz in this inductor model, right? So but what I'm saying is that don't do number crunching. Don't do number crunching. Don't go to deep learning way of fitting the model, okay, where there is a training sequence and they even don't have components which have physical significance. You have to put in the model with the physical significance, and that's the whole point I'm trying to prove here. Okay, so thanks a lot. So this is going to be my inductor model for the EM simulated model, and this is a 1 nanohenry model. So what is useful in this whole thing is that you should be able to design an inductor, so a custom inductor with any inductance, right? And you will come to know from EM simulation what that inductor value is, right? And then if you want a model, you can fit it, but usually the idea is in your matching, the inductor value should match the circuit inductor value. That's how your layout is going to be same as your circuit. So with that note, I am going to end this session here, right?